Hello guys, thanks for joining us again. This session is a physics GCSE session and it's going to be led by Preshayla, who is a student at the University of Loughborough. Over to you.
Okay, so what we're going to be covering today is basically speed, distance, time, acceleration, how objects move and how they change speed. So first of all, we need to think about scalar and vector quantities. Then we're going to move on to understanding the speed equation a little bit more and getting a bit more advanced with it. Then we're going to talk about distance time graphs and velocity time graphs and how we interpret the different features of them. We'll have a little bit of time for example questions, and then we'll take your guys' questions as well at the end. Okay, so the first thing we need to think about is this difference between displacement and distance. So they're two different things because of the difference in their kind of meaning, but actually it's really easy to get confused between the two because they mean very similar things. So displacement and distance, I'm sure you've heard of before, probably being used interchangeably and not necessarily in the correct way. So we need to have a think about which one is a scalar quantity and which one is a vector quantity. So is distance scalar or vector, and is displacement scalar or vector? Put your answers in the chat or just have a think about it to yourselves. Which one's scalar and which one's vector? Cool, I can see lots of you putting the correct answers. So yes, distance is a scalar quantity. Now a scalar quantity means that it has no direction, it's just value. It doesn't really mean much, it just means the distance that the object moves. So it goes from point A to B, how far was it? Was it 5 meters, 10 meters, 60 kilometers? It's just a distance. The number and the unit, and that's it. We have no idea what direction it went in, and that's called a scalar quantity when it has no direction associated with it. Now displacement, as you guys said, is a vector quantity. Now a vector quantity does have direction, so it's the opposite of a scalar quantity. So displacement is the vector version of distance. It has direction, we know what way it went in, as well as knowing how far it went. So for example, a distance would be 6 meters and that's it. Displacement could be 6 meters north, 6 meters on a bearing of 45 degrees, 6 meters left. It has to have a direction associated with it because it's a vector quantity. Okay, so that's the difference between displacement and distance. Displacement has a direction attached to it, distance doesn't. Okay. Now we have the same thing with speed. You might have heard the terms speed and velocity, again being used interchangeably, but they actually do have different meanings. So speed is the scalar quantity, whilst velocity is the vector quantity. Now we need to know a few common speeds kind of in our daily lives. So we need to know what speeds we have where, what kind of is the speed of walking, what is the speed of running, what's the speed of sound. We need to know these common speeds to be able to compare between different speeds. Okay, so in an exam, they might ask you, okay, what's the speed of this plane? And then they say, compare that with the speed of a cyclone. Compare that with the speed of sound. So we need to know these 4 common speed. Walking is roughly 1.5 meters per second. Running is roughly 3 meters per second. cycling is roughly 6 meters per second, and sound is roughly 300 meters per second. So that's just kind of, you need to memorize it. Remember that it's not always going to be exactly equal to 1.5 meters per second or those speeds. It's just kind of a rough estimate of the average person. Now, speed is actually rarely constant. It's very unlikely and very rare for a speed to actually be constant in our day-to-day lives. So if we think about a moving object, example, a car, that's always changing speed. The speed of sound, that always changes speed. The speed of sound in air is different to the speed of sound, for example, in a solid or a liquid. Speed of wind, always changing. Okay, so we need to understand that actually, realistically, speed is rarely constant. But in a GCSE, they kind of take the assumption that speed is constant. And so you kind of need to understand that realistically, it's not going to be constant all the time. But in a GCSE, they are going to assume it's constant a lot of the time. Okay. So they might ask you, for example, why is this assumption of speed being constant incorrect? And then you'd say, well, in real life, actually, speed is rarely constant. Everything always kind of changes speed. So that could be a question that they ask you. Now we have two types of speed. We have average speed and we have instantaneous speed. So average speed is the speed kind of over a period of time. So from 0 seconds to 30 seconds, what speed were they doing? What speed was the car doing? Instantaneous speed is the speed at one specific point. Okay, so let's say the car passes, I don't know, a bus stop. When it passes a bus stop, it has an instantaneous speed. What is the speed at that point? Okay, so when it passes a bus stop, what is the instantaneous speed at that single point? However, an average speed is an average of the car's journey. Yeah, so it's an average speed of the car's journey. So from point A to point B, what was the average speed that they were doing? So it takes into account a lot of different speeds. Whereas instantaneous speed is just one speed at one single point. Okay, so velocity is this speed, but with direction. Velocity is the vector kind of version of speed. Now, we need to think about velocity in a circle. So think about an object that moves in a circle. So for an example, a car on a roundabout. Okay, a car on a roundabout moves in a circle. It has circular motion. Now, yes, it maybe stays the same speed, right? So let's assume that it stays the same speed as it goes around the circle. Let's say it does 10 miles per hour. So it does 10 miles per hour as it's going around the circle. The speed never changes. But the car is constantly changing direction. So it might be facing forward and then turn left, and it's constantly turning, right? To go around a circle, we have to constantly turn. We have to constantly change direction. So although our speed stays the same, our direction doesn't. And therefore, the velocity changes. Okay, so although the speed, the value is the same, the direction is always changing. And therefore, velocity is always changing, because velocity is speed with a direction. And if speed changes or direction changes, velocity changes. If one or the other or both change, velocity changes. They come hand in hand. If one changes, then velocity changes. If speed changes, velocity changes. If direction changes, velocity changes. And if both change, velocity still changes. And in our scenario of a car moving in a roundabout, the speed stays the same, how fast they're going stays the same, but the direction is constantly changing in every single point on that circle. So at one point, they're going to be facing that way, facing that way, facing that way, and constantly changing. And the direction constantly changes, so the velocity constantly changes. So we need to know this kind of scenario of what happens with velocity in circular motion. Okay, so speed stays the same, but the direction changes, so the velocity changes. And they could give you in the exam an example question to do with motion in a circle and ask you to explain kind of what happens, what's the motion of the object. So they could ask you to explain what happens with the velocity, what happens with the speed, what happens with direction. They could ask you anything about circular motion. However, do bear in mind that if you are doing a foundation tier exam board, then this will not come up. It's only for higher tiers that need to know about circular motion. Okay, so we have our speed, distance, time equation, probably the first equation that you learn in physics. It can be quite a basic equation, but actually the letters can be really confusing. And I definitely find this too, and I'm sure you guys will find it quite confusing too. The letters don't tend to match up with the words. So you might have learned it as speed equals distance times time. So you might have learned it as speed equals distance over time, right? That's the equation for speed. However, speed is with an S here, distance is with a D. That makes sense, right? Speed begins with an S, distance begins with a D, everything's fine. However, we now need to move on to this more advanced form of the equation, which takes into account vector quantities now. So I want you to forget whatever speed, distance, time equation you've learned previously and learn this equation only with the correct letters, because this is what is going to come up in an exam, and this is the equation that you need to learn. So forget this equation here. It's really misleading. We need to learn this new equation. It's the same equation, but the letters are slightly different because they mean different things. So for S is now not speed, it's distance. Okay, I know this is kind of backwards, but just bear with me. Speed is distance, okay? And the reason that we have S as distance is because distance is also displacement. So if you were doing this equation with vectors instead of scalars, then distance would be swapped out for displacement, okay? So we can replace distance with displacement. And the letter that we use for displacement is an S. I have no idea why, but the letter that we use for displacement is an S. Okay, so we need to know that S in our equation is distance and not speed. Now we move on to the second part, which is this V. V stands for velocity. But remember, if we're doing it with scalars, that could also be speed. So V is either speed or velocity. So that one's not so hard to remember because V is velocity and they do match up. Remember, that's measured in meters per second. Time, nice and easy. T, time, that one doesn't change, luckily. So T is time, and that's measured in seconds too. So the kind of thing that we need to get used to now, the new aspect of this equation, is actually putting S for distance instead of S meaning speed, which we previously had. Okay, so it's taking it to that next level to be able to include vector quantities. So remember that we can do the equation with distance equals speed times time, or displacement equals velocity times time. Okay, now some of you I know love to put your equations in triangles, which is a really great way of learning equations. So if you wanted it in its triangle form, what we're going to have is S on the top here, and then V here, and T here. Okay, so we're going to have S, V, and T, which makes sense because V times T is S. So it's really all about getting used to this S, meaning distance or displacement, instead of speed, because velocity is now V, which is speed. Okay, so SVT or S equals VT, however you want to learn it, the triangle or the letter equations as well. Okay, so moving on to distance time graphs. You may have seen these before, but it's basically a graph of distance against time. We plot distance on the y-axis, as you can see here. And this specific graph is in kilometers. There's not really a kind of prescribed unit that we use for distance because it really depends on what the question's asking. The standard one tends to be meters, but it's really important that in speed, distance, time questions, you pay attention to the units because they love to switch them up. So for example, you might have miles here, and you might have seconds here, you might have hours here, you might have kilometers here. So we have to pay attention to what the axis tells us. So for our x-axis here, we have it in hours, right? We're going from 9 a.m. to 10 a.m. to 11 a.m. and so on. So we need to pay attention to what the units are. In this example, we have kilometers and we have hours. And we have a plotting of the journey. Okay, so we have a nice graph of the journey that this specific thing has taken. Could be a car, could be a person. Okay, so if an object does move in a straight line, we can show it with this type of graph. If it's not moving in a straight line, we cannot show it with this type of graph because it's not a displacement time graph, it's a distance time graph. So only if it doesn't change direction can we show it on this type of graph. So if it moves in a straight line and doesn't change direction, we can show it in a distance time graph. And don't worry, in an exam, they would never ask you to plot a distance time graph of something that doesn't move in a straight line. Okay. So we plot distance on the y and time on the x so that the gradient is speed. Okay. So we have our equation S equals VT, distance equals speed times time, where we have distance plotted on the y-axis, time plotted on the x-axis, so these match here and these match here, so that we know our velocity will be our gradient. So it's setting this equation into the equation of a line so that we are able to plot it. And this is a technique that comes up a lot in GCSE Physics, is being able to take an equation and thinking about how it would work on a graph. So for example, we plot distance on the y and time on the x so that the gradient is velocity. Okay, now if you don't know what y equals mx is, don't worry, that's just the equation of a line. You will learn it in maths, but basically it just means that whatever you plot on the y equals the gradient times x. And we can rearrange it so that we have m equals y over x. So the gradient is the change in y over the change in x. That's how we find the gradient of line. So the gradient of a distance time graph is velocity. Okay, the gradient of a distance time graph is velocity or speed. Okay, so what do kind of the features of a distance time graph look like? We have quite a basic one here, but what does it actually mean? Well, a straight flat line, as you can see in the dark blue here, means the car is not moving. Time goes on, but distance doesn't change, right? It's not going up the y-axis, it's a flat line. Time goes on, but the car does not move. So the car is at rest or stationary. It has no speed. Okay, so from 11 o'clock to 12 o'clock, the car has stopped. It is at rest. If we have a straight slanted line, so for example, the green lines that you see here are all straight slanted lines. That means the car is traveling at a constant speed. The object is traveling at constant speed. So from 9 till 11, it's traveling at a certain speed. From 12 till half 12, it's traveling at a speed. And from half 12 till 2, it's traveling at a different speed. So the green lines means it's traveling at a constant speed. The speed doesn't change. It stays at the same speed for that amount of time. A curved line, like we see in the light blue, is a changing speed. The speed constantly changes, and this can also be known as acceleration. So if we have a changing speed, it's also known as acceleration. Okay, so changing speed can also be known as an acceleration. And that is depicted by the curved line in light blue. So you need to know what each of the features of a distance time graph represent, and we need to be able to interpret these graphs. So for an example exam question, they might ask, what does the dark blue line represent? It won't be in colour, but what does the kind of flat line represent? And you would say rest. What does the straight slanted line represent? Or what does this section of the graph represent? You would say a constant speed. If they give you a curved line on a distance time graph, that's acceleration, that's a changing speed. So we need to know what each of the features mean, as well as the fact that we can find the speed from a distance time graph by finding the gradient of the line. So how do we find the gradient of a line? How do we find the speed from one of these distance time graphs? Well, you might have done this before. Don't worry if you haven't, but finding the gradient of a straight line is pretty simple. We use another equation for it. So we're going to find the speed between 0 and 10 hours. So this portion of the graph here, between here and here, we're going to find the speed. We know it's a constant speed because it's a straight slanted line. A straight slanted line from 0 to 10 hours. So we're going to find the speed there. So to find speed, we need to find the gradient of the line. Gradient is the change in y over the change in x. So what we do is we draw a nice little triangle underneath the section of the graph that we're trying to find the speed of. So for example, we're trying to find the speed between here and here. So we're going to draw a triangle. So we're going to draw a line down which meets the x-axis and a line across which meets the y-axis. So it makes a nice little triangle. We are going to find the change in y and divide it by the change in x. So how high is our triangle divided by how wide our triangle is. So first of all, let's find our change in y. How high is the triangle? Well, it goes from 0 to 10 kilometers. So our triangle is 10 kilometers high. We do the same on the x-axis. We find the change in x, or how wide the triangle is. And we see that it goes from 0 to 10 hours. So our change in x is 10 hours. Now we need to divide them by each other. The change in y divided by the change in x. So we do 10 divided by 10 is 1. Not forgetting to put our units in, which is, in this instance, kilometers and hours. So our units of speed this time are kilometers per hour. But remember, the axis could be lots of different units, for example, meters and seconds, miles and hours, kilometers and hours, or any combination of any of the two. So we do need to pay attention. For this one, it's kilometers per hours. So we're going to do the values divided by each other and put the units on at the end. So for this example, it's 10 kilometers divided by 10 hours. So it does 1 kilometer every hour. That's how we find the gradient of a straight portion slanted line on a graph, to find speed given a certain distance, given a certain time. Now for higher tier, we need to take it one step further. We need to be able to find the speed from a distance time graph when it's a curved line. Okay, so if it's a curved line, that means an acceleration. That means a changing speed. Okay, so the speed is changing. It's not constant anymore. It's a changing speed. So we want to find the speed in this section of the graph. Okay, now yes, it's not exactly a straight line. So it is kind of an estimation that we're doing here. It's not exactly a straight line, it is a curved line, so we need to put a straight line on it. Okay, we can't find the gradient of a curved line. We can't do that. That's not until A level that you can do that. We cannot find the gradient of a curve. So what we do instead is we put a line next to it, which is really similar, right? You can see that they're pretty similar until you get to the edges. That is called a tangent. So tangent is this green line here, which we draw, and it's a straight line that touches a curve at a point. So it's a straight line that just touches the curve at a point and then extends either way, so that we can match the shape of the curve pretty closely. It only starts to change at the edges. So it's an estimation. It's not going to be perfect, but we use it so that we can find the gradient of that section of the graph. So that's the first step, is to draw a tangent to the curve. So the tangent to the purple curve here is this line in green. So our tangent is this green line here. We, again, can find the gradient of a straight line. And we do this in exactly the same way as we did before. So the only difference between doing it for a straight line and for a curved line is, for a curved line, we need to draw the tangent first. Once we've drawn the tangent, we can then find the gradient of the tangent like we did before. So the gradient of the tangent is the same equation, change in y divided by change in x. How high it is divided by how wide it is. So for this one, let's find our gradient. We're going to do the change in y. So from 20 meters to 140 meters. So that's 120 meters. Do bear in mind that this line does not go through 0. That's absolutely fine. You don't need to extend it all the way. We just want to take it from here to here, just where the kind of two lines match the most. Okay, so don't worry about going all the way down to 0. It's not necessary. You just need to get as big of a triangle as you can. So we use the same formula to find the gradient of this straight line here. And we're going to use change in y, which is 120, divided by change in x. So we're going from 4 seconds to 9 seconds. So our change in x is 5 seconds. So we divide them by each other. We have our change in y is 120 and our change in x is 5. When we do 120 divided by 5, we get 24, not forgetting the units, which is meters and seconds. So it's meters per second. Previously, it was kilometers per hour. This time it's meters per second. So the difference between doing it for a straight line's much easier. We just go straight in. We can find the gradient of the portion of the graph that we're looking at the speed for. So to find the speed, we find the gradient of the line. And for a straight line, it's pretty simple. We just do change in y over change in x. However, for a curved line, we need to draw a tangent first. So we draw a tangent and we find the gradient of that tangent in the same way that we do for a straight line. So we cannot find the gradient of the curve. We can only find the gradient of the straight line. So we need to draw a straight line, then find the gradient of that straight line in the same way. Okay. Now do bear in mind that a curve, although it means a changing speed, so curve lines mean a changing speed, the speed is pretty much constant in this portion of the graph, right? From here to here, the speed is pretty much constant. It's pretty much a straight line. So we're making an estimate. We're pretending that it's a straight line, okay? And we're finding the speed at that point. So although curved lines do mean changing speed, in that section of the curved line, it's pretty much constant. So we draw a straight line and then we find the gradient of that. Okay, so acceleration and deceleration. We have a new formula that we need to use. So acceleration, it can also be switched out for deceleration. Acceleration means getting faster, deceleration means getting slower. So acceleration is change in speed divided by time. Okay, so change in speed divided by time. Change in speed can also be known as final speed minus initial speed divided by t. So we have this triangle here. This triangle is called delta and it means change. The symbol, the triangle, means change. So delta V is the change in velocity or speed. Now, the way to work out the change in speed is by doing the final speed minus the initial speed. So final speed is V. And initial speed is denoted by a U, just because we couldn't use V for both. So we use a U for initial speed. Okay, so final speed is V, initial speed is U, final speed minus initial speed gives us this change in speed. Then we divide it by time. The units for each section of that equation, well, acceleration, which is A, is meters per second squared. The change in velocity is still meters per second. And time is just t, which is always measured in seconds. Okay, so we have our change in speed divided by time is acceleration. New equation, but not too complicated, hopefully. Okay, so let's move on to velocity time graphs. So different to distance time graphs. Now we're plotting how the velocity changes with time. Okay, so how does the velocity change with time? So completely different features, which mean completely different things. So it's very, very easy to get confused between the features on a distance time graph and the features on a velocity time graph. So it's important that you separate them out and notice in an exam question, is it talking about a distance time graph? is it talking about a velocity time graph? And use the correct features that match up with the graph. Okay, so this time for a velocity time graph, if we have a straight flat line, so this portion in the middle here, if we have a straight flat line, that's a constant speed. There's no acceleration, there's zero acceleration. It's not getting faster or slower, it's the same speed for that entire portion. Okay, so it's the same speed for that entire portion. The straight slanted line now means a constant acceleration. It's getting faster constantly in the same way. So it might get faster by 3 meters per second every second. So the car starts at 7 meters per second. It wouldn't be a car, let's say a bike. So a bike starts at 7 meters per second, 3 seconds go, and the bike increases by 3 meters per second, increases, and it increases in the same way. That's a constant acceleration. It's getting faster in the same way. So that's a straight slanted line. The gradient of this graph is acceleration. So completely different to a distance time graph. In a distance time graph, a straight flat line meant rest. The car's not even moving. In a distance time graph, a straight slanted line meant a constant speed, and a curved line meant acceleration. However, in a velocity time graph, a straight flat line means constant speed, a straight slanted line means a constant acceleration, and the gradient can be interpreted as acceleration. Okay, so gradient is acceleration. So if we do change in y over change in x, we're not going to get speed this time, we're going to get acceleration. Now there's one more thing that we need to know, which is for higher tier. So if you're higher tier, you need to know this one. If you're foundation, you only need to know these three. So the area under a velocity time graph has significance. In a distance time graph, don't worry about it. It doesn't mean anything, you don't need to know about it. In a velocity time graph, we need to know what the area under the graph means. And that is actually the distance elapsed. So how far the car has travelled is actually the distance under the graph, the area under the graph. So to find the area under a velocity time graph, what I would do for this specific graph is probably split it up into 3 segments. I split it up into a triangle, a rectangle, and then another triangle. I'd find the area of the rectangle just by doing base, which is 3, times height, which is 8. Then I'd find the area of each triangle by doing base times height divided by 2. Okay, so it does rely on you knowing your equations for the area of a rectangle and the area of a triangle, which I'm sure you know, is base times height for a rectangle and base times height divided by 2 for a triangle. So you may have to interpret the distance from a velocity time graph, which is the area underneath the graph. And what I mean by the area underneath the graph is this shaded section here. So all of this is the area under the graph. Okay, so you need to find the area of this whole section. Okay, so the area under the graph is the distance. So we can probably going to have to split it up because it's not ever going to be a rectangle. It's just too kind of basic for an exam question. They're probably going to do some kind of compound shape where they go for like a triangle or a rectangle triangle or a mixture of the 3. Just need to be comfortable on how we can split a velocity time graph up to find the area underneath the graph to then interpret it as distance. Now you can see that a line sloping upwards is a positive acceleration, but a line sloping downwards is a negative acceleration. And that's another thing that we need to know is if the line slants towards kind of the right, that's it getting faster. If it slants downwards to the left, or however you want to remember it, it is getting slower. A negative acceleration, or sometimes called a deceleration. So on the left, we have a positive acceleration. On the right, we have a negative acceleration. So that's another feature of the velocity time graph that you need to know. So how I would recommend kind of learning the differences between the two is probably by kind of visually drawing it out. So having two separate posters in two separate locations, don't have them next to each other because you will get confused. Making like a poster and a distance time graph, color coding it, and showing what each feature of the graph means. So a flat line, what does that mean? Slanted line, what does that mean? What does a gradient mean? How do we work out the gradient? Then have a separate poster for the velocity time graph, what all the features mean, color code it, and put them in two separate locations. That's how I would suggest learning these, because it can be very, very confusing if you don't know what the features of the graph mean. Because they're very similar features with very similar meanings, very easy to get confused. Okay, so now we have a third equation for the session. I promise it's the last one that we need to use. And it is probably the most complex. And what it is another, it's another equation for acceleration. Okay, it's another way of working out acceleration, but just with more terms, with more things in it. So for this one, we have the final velocity squared minus the initial velocity squared equals 2 times acceleration times distance. So remember, that's s, it's not speed, it's distance. So this is our equation for constant acceleration. Somebody put in the chat, is this SUVAT? This one, yes, is a SUVAT equation. Don't worry if you don't know what SUVAT means. It is an A-level topic, but for the person who asked, yes, this is SUVAT. But yeah, it's just a kind of more complicated equation with more terms to work out acceleration. Now, because it is such, it's got such a lot of terms in this equation, it can be hard to rearrange. So what I suggest for this equation is being really comfortable in how to rearrange it. So you need to be able to rearrange it for V, for U, for A, and for S. And that can be complex. So we're going to rearrange it for V, just so you can see how it would be done. So we're going to rearrange it to get V alone. So let's say we're trying to work out final velocity, where we know that we need to rearrange the equation to make final velocity the subject. So first of all, we're going to take our U squared to the other side. We're going to add U squared to both sides to get rid of it on the left-hand side and add it to the right-hand side. So we get 2AS plus U squared. Then we need to get V on its own, but right now it's with a squared. So we do the opposite of a squared, which is a square root. So we square root the left-hand side to get just V, and we square root the right-hand side to get the square root of all of that, 2AS plus U squared. Okay, so you need to be able to rearrange it for any of those letters, A, S, U, or V. Now, you also need to know that for any object that falls on this planet, on this Earth, close to the ground, has an acceleration of 9.8 meters per second. It does not matter how heavy the object is. And you might have heard of that famous experiment on a tower. They dropped two objects from the top of the tower. So I think it's a feather and a brick, and they drop them and they reach ground at the same time, right? And that is because they have the same acceleration. Doesn't matter the object, it accelerates towards the ground at the same speed. Okay, so 9.8 meters per second squared for an object that accelerates on this earth. So if you drop an object, it's going to have an acceleration of 9.8 meters per second squared. And you will commonly have to use 9.8 for the acceleration in this equation. So if an object is falling, it has an acceleration of 9.8 meters per second squared. Okay, so that is all the content. If you guys have any questions, put them on the chat, put them on the Q&A. I'll take some questions now. If you want me to go back to the slide, then just say. So someone said, what would a curved line be in a velocity time graph? Well, a curved line in a velocity time graph doesn't actually have any relevance. That's why I've not included it. It's just not relevant. It doesn't mean anything. I mean, it means a changing acceleration, but that's so advanced that you don't even do it at A level. So don't worry about that. But a curved line would mean a changing acceleration, but it bears absolutely no relevance, and you don't need to worry about it for your GCSE. What topic is this under? This is under the forces section of AQA exam board, but for other exam boards, it will just be under forces. Forces in motion, forces, something like that. Somebody said, can you find the equation of the curve and then substitute time into it to find distance? Yes, you can find the equation of the curve, but sometimes they won't give you enough information to do that, and they definitely would not expect you to do that. They would not expect you to find the equation of the curve at all, so really don't worry about that. It's going to be very, very difficult for you to do that in a physics exam. So yeah, don't worry about that. Just draw a tangent and find the gradient of the tangent. Someone said, can you go back to the displacement graph? I don't know which one you want. I'll just put that one up for now and then let me know if it's a different one that you want. I think that's all the questions.
I've got a few more here.
Yeah.
Oh, someone asked what's the difference between the speed of air and the speed of wind. I think it's related to your first slide or so.
Yeah, okay. So the speed of air, we don't really have the speed of air. We have speeds of things in air, but we don't really have the speed of air itself, right? Because air is kind of just, it's just static, right? There's not really any way to measure the speed of air. We can measure the speed of wind, however. I don't really know how they do it, but they do it with knots, and how fast the speed of wind is done with knots. However, we don't really have a thing that is the speed of air. We just kind of do it with the speed of wind. However, we do have the speed of sound in air, the speed of sound in air, the speed of sound in air, and the speed of sound in light. I don't know what's going on. The speed of sound in air and the speed of light in air. So you need to know those two values. So the speed of sound and the speed of light in air, but not the speed of air itself. Hope that makes sense.
Great, thanks for that, Preshayla. There's another question. Well, it's more a request for a quick summary of instantaneous speed.
Okay, so yeah, we have two different things, which is the average speed and the instantaneous speed. So the instantaneous speed is how fast it's moving at a single point. Okay, so let's say we have a car, it goes from A to B. It travels, let's say, 6 kilometers in a certain time. We can find the average speed just by doing distance divided by time. That's the normal average speed. However, the speed of that car most likely changes from A to B, right? It's probably not going to go at constant speed. It might need to stop, might be a car in front of it, they might slow down for whatever reason, they might go faster. So there might be a few different speeds in A to B. And let's say we wanted to find the speed at an exact point. So this is what a speed camera does. The speed camera measures your speed at an instant, right? At an exact point. It takes a picture and it measures the instantaneous speed. The speed that you were doing at the exact point the camera took the picture. That's instantaneous speed. How fast you were going at that exact point. Hopefully that makes sense. Someone said, are there objects that don't accelerate at 9.8 meters per second squared? So when objects are falling, they will accelerate at 9.8 meters per second squared. This is because of gravity. This is because the gravitational pull of the Earth, that objects do accelerate towards the Earth at this specific value. However, yes, there are objects that don't accelerate at 9.8 meters per second squared. If it's not falling, then they can do kind of whatever they want. So whatever acceleration they want, because they're not kind of bound by gravity. However, if gravity is acting on that object, then it will fall at 9.8 meters per second squared. Okay, I think if that's all the questions, we'll move on. Okay, so I've got a few quick fire questions for you guys, just to consolidate what we've learned today. So if you could put your answers in the chat, please, for these two questions. What is a typical walking speed, and what quantity is the rate of change of velocity? By rate of change, we just mean divided by time. Rate just means divided by time. Okay, so for the first one, we said 1.5 meters per second, not very fast. The typical walking speed is 1.5 meters per second. And for the second question, it is acceleration. So acceleration is the rate of change of velocity. That's how it's defined. It's how does the velocity change over time. Okay, how is speed found from a distance time graph? And how is velocity found from a velocity time graph? I'll give you 1 minute to think about this one because it can be a little bit tricky to remember them in the beginning. So how is speed found from a distance time graph? Cool, so the gradient of a distance time graph gives you the speed, and for the velocity from a velocity time graph, well, you just read off the x-axis, the y-axis. Okay, how is acceleration found from a velocity time graph? So yeah, the gradient of a velocity time graph is the acceleration. And what is the acceleration of a horse that accelerates from rest to 4 meters per second in 8 seconds? Okay, so this question is done using our new equation for acceleration, which is A equals V minus U over T. So our change in velocity is our final velocity, which is 4. So it goes to 4, that's the final velocity, minus the initial velocity, which is rest, so 0. We put that all over over t, which is 8, so 8 seconds is our time. So 4 divided by 8 is just 0.5 or a half. Remember, acceleration is measured in meters per second squared. So our final answer is 0.5 meters per second squared. Well done if you got that. It wouldn't be appropriate to use our other equation for constant acceleration. So remember, our other equation is the v squared minus u squared one. But it wouldn't be appropriate to use that because we don't have any distance. Okay, so if we don't have any distance, we can't use that equation. Okay, what is the unit of acceleration? I just told you this one. So yes, the unit of acceleration is meters per second squared. What is a typical speed for a bicycle? Typical speed for a bicycle. Cool, so the speed of a bicycle is 6 meters per second. Okay, so I just wanted to give you guys these QR codes, which are links to more exam questions. So questions that will actually come up in an exam. There are a few different ones in here. So speed, one's about acceleration, one's about distance time graphs, one's about velocity time graphs. So if you just scan this off of the screen, hopefully it will work, and you'll be taken to a link, because I know that sometimes it's hard for you guys to find resources. So I thought I'd just give you them. Have a go at them. The mark schemes are on the website. They are taken from Physics and Maths Tutor, and they are for the AQA exam board. However, when you're on the website, you can get access to other exam boards. The content is really, really similar for this topic, which is good. So you've got lots and lots of questions that you can be practicing. Yeah, so do bear in mind that there were some stuff that we covered which was only for higher tier, which is the circular motion. So how does velocity change in a circle, and finding the gradient of a curved line. So those two things you only need to worry about if you're higher tier. Cool, so if you do have any more questions, put them in the chat. Someone said, how many forces are there? Too many to name, really, is the answer to that question. You've got gravity, you've got pushing, pulling, bending, stretching, compressing. You've got frictional forces, you've got electrostatic forces, electromagnetic forces, you've got nuclear forces. There's I probably didn't answer that question, like countless. What exam board is this? All the webinars that I do for physics are based on the AQA exam board, but a lot of the material is overlapped with other exam boards. Someone said, is calculus similar to this? Yes, calculus is very similar to when we were finding out the gradient of the curve. So if you know what calculus is, then yes, this is exactly what we're kind of doing here. Do we need to know about SUVAT and what equations does it consist of? You do not need to know about SUVAT. If you know about SUVAT, great, but don't worry, you do not need to know it for GCSEs. They only come into A-level physics and A-level maths. However, this equation here, this constant acceleration equation, is an example of a SUVAT equation. So if you know what SUVAT is, fine. If you don't, you don't need to worry about it. But yes, this is an example of a SUVAT equation. The SUVAT equations are only applicable to when acceleration is constant.
Amazing. That takes us to the end of the session. Thank you very much for this lesson, Preshayla. It's been amazing. Thank you for the resources you shared. Thank you, everybody, for joining us. Have a lovely afternoon.
Thank you.
Bye all. Bye.
Bye.